is on parametric equations. And the entire chapter is on parametric equations. There's going to be a lot of stuff on conic sections, and you won't need to necessarily remember everything you've ever learned about conic sections. Conic sections are parabolas, ellipses, hyperbolas. But as we go through the chapter, you might need to be reminded of some of those rules. And most of what we're doing is going to be on the calculator. So if you know what to plug in the calculator, you can get through this. Just like polar equations, parametric equations do a very good job of graphing non-functions like ellipses and other conics. So you could see in here, the beginning part is learning about parametric equations, and the second part is about parametric conics, and so we'll talk about that. Okay, so parametric equations in motion in your book is section 6.3. So if you wanted to read the book, you can always do that. I wrote here, parametric equations are useful in a variety of scenarios. They can be used to express the coordinates of points that make up a geometric surface and blah, blah, blah. There's a bunch of stuff about 3 dimensions in physics. The most common use is location of object over time, and that's what we're going to talk about today. They're used to easily graph non-functions in mathematics, so like circles, things that don't pass the vertical line test. So I wrote the definition of conics, and I said the graph of the order pairs xy, so we're still going to be on the xy plane. We're not going to be on a new plane like we did with polar. I switched to a different plane where x equals f of t and y equals g of t. So now we're, instead of thinking of x as the input and y as the output, you're going to have this new value t, that's the input, and you have two outputs, the x value and the y value. We call the interval of t values, the interval, and we call t the parameter. You can read this again when it's all said and done. So I want to start with projectile motion. So I wrote projectile motion is a great way to begin learning about parametric equations. And you're not going to need to memorize this formula, so you don't have to worry about memorizing it. But it's nice to understand. So it says a projectile is launched at a height of h sub o, that's like original height, feet from the ground at an angle of theta with the horizontal. The initial velocity is v sub o, that's an o for original, it's an original velocity. So those are the starting height and starting velocity. We're doing feet per second. I know that those of you who do physics might usually use meters per second, but it's not that much different in meters per second. And the path of projectile is modeled by the parametric equations. So when you were in algebra, you might have done projectile motion, and your teacher might have said, you throw something in the air and it makes a parabola, and the graph is a parabola, and you said, okay, it sounds right to me. But when you were doing these in algebra, this axis was distance. Don't write this down. But this axis wasn't distance, it was time. So really, you were talking about time and then how high the thing was, height. I wrote distance, but height, same thing, over time. So the parabola was not an illustration of the path that the projectile makes. For any point, it's what time it is and how high it is. Okay, so the algebra version of projectile motion is different than what we're talking about, where both axes are distance. So the x-axis is how far horizontal the thing is going, and the y-axis is how high vertically, the height the thing is going, and the t is the time, but there's not a t-axis. So every point, you could draw this if you want, every point is going to have an x and a y associated with it, and also a t value. Okay, So t would be equal to some number. It's not a axis. So you might say at a time of 2, this is where the projectile is. Okay? And I made up a problem. We're going to graph it on the calculator and kind of play with the calculator. You'll see some similarities to polar. So I wrote a cannonball is fired from a position on a mountain. The initial height is 2,000 feet. So this is starting at a very high initial height. If you think about like shooting a basketball, that would be, like 6 feet or some, 5, 6 feet, depending how tall the person is. You're not shooting off the ground. If you're hitting a baseball, maybe you're hitting it at an initial height of 2 feet. If you're golfing, that's hitting the thing off the ground. The ball is getting hit off the ground, so maybe the initial height is 2 inches or directly off the ground. But the initial height is where the thing leaves. And so this cannonball is leaving a mountain, so it's way up above, so what would be like sea level. And that's got initial velocity and the angle of the cannon when it's initially fired. So that initial velocity changes right away because as soon as it's fired, it starts slowing down because of gravity. The angle changes because of gravity. This -16, that's part of this, is the force of gravity. So if you were not doing feet per second and you were doing meters per second, it would be a different number. If you're doing feet per minute, it'd be a different number. If you're doing miles per hour, it would be a different number. Okay. So we have to first set this up, then we'll put it in the calculator. So the x would be the original velocity, 200 feet per second, times the cosine of 65 degrees. And I intentionally made it a non-unit circle value. So this is just equal to some number. Okay, whatever that number happens to be, that is the vertical component of this. And then you can put that times t, and then y equals -16t squared, that's always there, plus 200 sine 65 degrees times t plus original height, which is 2,000 in this problem. So we're going to do this on the calculator, but if I wanted to know the position of the cannonball at 1 second, I would plug 1 into these. If I want to know the position of the cannonball at 2 seconds, I plug 2 into these. It has 2 positions. How far horizontally the thing is moving, this way, and how high it is off the ground. So there's 2 different numbers associated with that. So we're going to draw a sketch on paper, but we're mostly going to be doing this on the calculator. So you can draw 2 axes and you can label this height. And this would be the horizontal distance. So this would be the location, in the air. And like I said, when you did parabolas in algebra where this axis was time, it wasn't really modeling the shape. It was just telling you the height and the time. So this is a little bit different than maybe what you've done in the past. Okay, so now we have to type these into the calculator. All right, so go to mode and change it to parametric mode. The reason that we're gonna have a little bit of issues is because radian mode in general is better, but we have to use degree mode because we have degrees in the problem. Okay, the problem with degree mode is the same problem with polar. When you do zoom 6, it sets the step to 7.5, which is not a great step. So we'll hit zoom 6, but we're gonna have to adjust it. We need degree mode because we have degrees in our problem. So we're going to be in degree mode. And then if you notice when you hit y equals, you have an x and a y, and there's a little t here. T is the most common parameter, but that extra variable could be any letter. Okay, T is the most common one, but it could be anything. And you'll see problems where that parameter is theta this chapter. So anyways, let's type it in. Try to get the parentheses right. You can look at mine. The way you get the T is by hitting that same button that you used to use for X. So this button, if you press it in function mode, it's X. If you press it in parametric mode, it's capital T. I know we wrote lowercase t. I don't know why they chose it to be uppercase T, but it doesn't really make a difference. And then in polar mode, it would be theta. So let's say you're doing a problem where the parameter is A. You still have to use T in the calculator. If the parameter is theta, you still have to use T in the calculator. Having theta in the problem doesn't mean it's polar. And we'll cross that bridge when we get to it. But that button in parametric mode will always say T, and it's got to be T for the parameter. Just like when you're graphing in function mode, you need to use X and Y. You don't really have a choice. You can't use different letters. Okay, so negative 16t squared plus 200 sine 65. So if you're doing a problem that has no degrees in it, it's just a problem that is parametric, radians is a better choice. If there's no trigonometry involved in it, or not specifically degrees, it's a better choice. But we don't really have a choice because these 65s are in degrees, so we need to be in degree mode. If you type something in for X and nothing in for Y, you'll get an error. You need to have something in for X, something in for Y. Now, I'm going to do zoom 6, but we're not going to even see anything. But start with zoom 6. Zoom 6 will be a good way for us all to start with the same window. Okay, so I have T min, T max, T step. These are the times. Again, that's not an axis. Then you have your normal x-axis and y-axis, so nothing unusual there, other than the fact that we can't see the graph at all. So this is going up to 360 seconds. That might be too much. How long do you think this cannonball will be in the air? Anyone make a prediction? 2 seconds, 5 seconds, 60 seconds? No one wants to say. 20? How many? 20 seconds? All right, we'll type in 20. And if it's wrong, we'll just change it. This is a terrible T-step. This is going to graph 0. That's going to jump to 7.5. And then it's going to do 7.5 more, which would be 15. And we'll have 3 dots, and it'll connect the dots. It'll be terrible. We don't want to make it too low, because remember what happened with polar. If you make it too low, the graph goes really slow. Okay, so let's just go 0.1. If you're in doubt, 0.1 is safe. That's about what the default is in radians. Okay, so the x min, I'm gonna make 0, because I know this cannonball is moving horizontally. How high do you want to make that x max? Anybody want to make a prediction? All right, I'll put in 200. Maybe that's a terrible one, I don't know. For the scale, I can just put 0 in, it won't even have a scale. It's fine. All right, now I know this thing starts 2,000 feet off the ground. That's a starting height. And I know that it's an angle of 65, moving 200 feet per second to start. So how high do you want to go on the y max? You're just making a guess here. Say it again. 22? All right. So we'll see some of the graph for sure, and then we'll adjust it if it's no good. And then the scale, You can just put 0 in there. Let's see what we got. All right, so I got, here's where it leaves. It goes da, 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 and then it leaves the graph. Okay, so what should I change? The Y max for sure. How high do you want to go? You can go a little crazy here, okay? Yeah, 2,500. That might be enough. Let's go 3,000. Let's live life dangerously, okay? If it goes too high, we can always go low, but at least we'll see it. Now it's going like this. The projectile's going like this. So could we just assume this cannonball just keeps getting higher and higher and higher and just goes on forever? Okay, we need so what do I need to change now? The X max. How high do you want to go? This one am I changing, or am I changing this one? Is it this one to 1,000? The X max. Okay, X max. All right. Because I want to move, I want to see more to the right. I don't know if this step is too high or too low yet. Well, this is looking good. Okay, I want to see more. So what am I changing now? X max, how high do you want to go? 2,000. Yeah, exactly, 2,000. Let's go crazy. Don't just go by ones, you know, or tens. Oh, look at that. That was beautiful.
What happens if I can't see like the graph at all? Like it's just blank.
You have this window? Oh, that's not good. So, couple of things. If there's a difference between something's wrong right now or you can't find it. If let's say you have no idea where the graph is, try to hit trace, and when you hit trace, these numbers will pop up, and you can find, you know, where the Y is and adjust. So if you can't find it, hit trace. If you're doing what we're doing and you can't see it, you probably typed the thing in wrong. That's my guess. You want to just try typing it in again? And then seeing it. Okay, now remember, you actually have the little ball animation that you can use. And so this is a good way to visualize what's going on. And when I hit graph, you can see it like a cannonball. Now this always moves slower for whatever reason. Having the ball without the line is, you know, not super helpful. Now let's hit trace and take a look at the points, okay? These are not your typical XY points because every point has a T value associated with it. So this T value of 3 is, what's 3 what? 3 feet, 3 cannonballs, what is it? No. 3 seconds. All right, we got it. 3 seconds. So that's the time. So the cannonball fires. There's where it is at 3 seconds. That's how far horizontally from the mountain, the base of the mountain, I guess would be. And this is how high in the air it is. So every point has a T associated with it. Now, if you go to second calculate, you'll notice a bunch of things missing. The max and min function's not there. The zero function is not there. You only really have value. These are calculus formulas that you haven't learned yet, but you have value. And so you can only plug in values like, I want to know where the cannonball is at 6 seconds. And you can type in 6 and it will tell you. If you wanted to know the max and the min, you'd have to convert this thing to rectangular. So you'd have to convert it to not being parametric, which we'll learn how to do. And then you could use the max min functions of the calculator to do that. Are there any questions about any of this so far? Yes. You can't find yours? Okay, I'll come look at yours in a second. So we really have much left here. So I want you just to draw a sketch of this, and you don't have to have it perfect. That would look terrible. This initial height is 2,000. And we could trace this thing and figure out where it lands. It's just that finding out where it lands, the calculator doesn't do a great job of. So that's you know, one fault of the calculator is that you'd have to trace and estimate because it doesn't have a zero function. And our 20 was a really good estimate. So I just want to show you a couple things. I know a lot of you might know this, but I'm going to show you a couple things. This is very similar. If I do 10 seconds only, this thing is going to graph and just stop at 10 seconds and I won't see the rest of it. Okay, so that's what happens if you don't have the step big enough, similar to polar. If your t-step was 7.5, I just want to show you what this looks like. Let me get rid of that. Well, actually, let's leave the ball there. I'm kind of curious what this looks like. It goes really fast. It plots a point, plots a point, plots a point, connects the dots, and just stops. If you're wondering like why I didn't see more of this, is because I have this at 20, so it plotted 7.5, 15, and the next one would be 22.5. So it didn't plot that point; it just stopped. And here's if I go further, that point would be down here, but you want that step to be bigger. So the default in degrees is this, not a good default. Don't make it too low. So that's it. That's all I wanted to show you on the calculator. Obviously, there's going to be more to learn than just that. We are going to learn next converting, and we're going to spend, quite a bit of time on the converting part of this. And then we're going to learn about conic sections and how to graph those in parametric mode. And that will be the chapter.